In this video, we are going to learn about Maxwell and Fulkerson algorithm for solving this problem. This algorithm dates back to 1950s. Before I start, due to the 10-minute time limitation, I will not be going into a great depth about the algorithm, but instead give a general outline on how it computes the max flow. The basic problem is to figure out how to send the flow between particular edges in a graph while obeying the capacities and then maximizing the amount of flow that goes from the source to terminal. Here are some of the terminologies I will be using in my example. Capacity constraint. The flow along an edge cannot exceed the capacity an edge can handle, so a flow of bigger than 20 is not possible for this edge. Flow conservation. This is the sum of flow going into a node is equal to the sum of flow going out of a node. So if a flow of 20 and 10 is going into this node, then 30 must come out. Residual network is a graph that gives the remaining capacities. Augmenting path is a direct path from the source to sink in a residual network. Residual capacity is the edge with the lowest capacity in an augmenting path, often called bottleneck. You will understand this more when I go through them in the example. Our goal is to find a maximum flow between the source and the terminal. So how would one calculate the maximum flow for this graph? Well, the first thing that comes to my mind is to choose a path from a source to terminal and allow flow through it and repeat this until I can push no more flow. So let's try this and see what happens and what problems we face. So this is the path I've chosen. It is a direct path from source to terminal, and this is called an augmenting path. Next, we allow flow equal to the residual capacity through this augmenting path. The residual capacity is the maximum amount of flow we can push through. In this case, the maximum is 20 that we can push through this path. Once we have calculated the residual capacity, we work out the residual graph, which is just the remaining graph with the remaining capacities. In this case, if we push a flow through of 20 through this path, the remaining capacity is 0. Again, the remaining capacity is 0. In this case, if we push a flow of 20, the remaining capacity will be 10. So in the next slide, I'll show you how our residual graph looks like. So this is our residual graph with our remaining capacities. We repeat step 1 and find a new path from source to terminal. So this is our new path. Again, we work out the residual capacities for this path again. In this case, it's 20 because this is the maximum amount of flow we can push through. And we work out the residual graph again. So this is our remaining capacities. And then we repeat step 1 again. We find a path from source to terminal. There exists a path. So we choose that. And we allow a flow of equal to the residual capacity. In this case, the residual capacity is equal to 10 because this is the maximum amount of flow we can push through this path. And we calculate the residual graph again, and we repeat step 1, which was to find a path from source to terminal, but there exists none, so we finished, and our output maximum flow for this is 50. Okay, so we got lucky in this case. We know the maximum flow for this graph is 50 because S is not pushing out any more flow. But the question is, does this always work? Let's pick a different initial augmenting path and see if we face any problems. Okay, so step 1, find a direct path from S to T. This is the path I chose. Step 2, allow a flow equal to the residual capacity through this path. The residual capacity for this path is equal to 30 because this is the maximum amount of flow we can push through. Step 3, repeat step 1 for the leftover residual graph. This is what our leftover residual graph looks like, but as you notice, we are stuck as there are no directed paths from S to T. And as we saw from our last example, we know 30 is definitely not the maximum flow for this graph. So this is where the Fulkerson algorithm comes in. It gives us the possibility to use a backward edge here and here, and this allows us to solve these kind of problems. Let me show you how in my next example, but first I will go through the algorithm briefly. So that's the algorithm. We start with no flow and we look for an augmenting path. As long as there is an augmenting path from source to sink, we compare the residual capacity of all the edges in the path, add the smallest residual capacity to all the edges in the path, and we repeat until no more augmenting paths are left. You may be wondering, this is exactly what we have done in our previous examples. So how is this algorithm any different? Well, you are correct. This algorithm is very similar. The only difference is how we create our residual graphs. This is our new approach to building the residual network. We calculate two kinds of edges, a forward edge and a backward edge. The forward edge is equal to the capacity minus the flow, and the backward edge is equal to the flow. So here is an example. We have an edge which has a capacity of 30 and a flow of 20 going from A to B. To calculate the residual network, first we calculate the forward edge, which is equal to the capacity. So the forward edge is 30 minus 20, and the backward edge is equal to the flow. So it has the backward edge of 20. Now I will go through the same example we did earlier, choosing the same paths where we got stuck, and see how the Fulkerson algorithm handles that problem. So this is the same example with the same starting path where we got stuck earlier. Our next step is to calculate the residual capacity of this path, which is equal to 30 because this is the maximum we can push along this path. So after this we will calculate the leftover capacities, which is the residual network, and from source to B the forward edge would be equal to the capacity minus the flow. So 30 minus 30 is 0, and the backward edge is equal to the flow, so backward edge would be 30. The forward edge from B to C would be 40 minus the flow, which is 30. So forward edge is 10. The backward edge is the flow, so 30. Again, for C to terminal, the forward edge would be 0 and the backward edge would be 30. So this is what our residual network looks like, with the backward edge of 30 and the forward edge of 10 from B to C. As you may have noticed, this is where we got stuck earlier because there was no directed path from source to terminal. But the Fulkerson algorithm avoids this, and instead we can use the backward path from C to B to complete the path. So this is what our new augmented path would look like. What a backward edge really allows us to do is, if you recall, we were initially sending 30 units of flow from B to C. So instead of sending 30 units of flow from B, it will instead send 10 units from B to C, and it will get 20 units from A. Notice C is still in equilibrium as 30 units flow in and 30 units flow out to the terminal. But now B has 20 units extra which it has spare to give to D. Our next step is to work out the residual capacity of the path and then update the leftover residual network. The residual capacity of the path is 20, as this is the maximum amount of flow we can push across this path. Next step is to work out the residual network. First we would need to work out the forward edge and then the backward edge. The forward edge from source to A would be the capacity 20 minus flow 20, which is 0, and the backward edge would be 20, which is equal to the flow. The forward edge from A to C would be 0, and the backward edge is equal to the flow, which is 20. From C to B, the forward edge is 30 minus the flow 20, so 10, and the backward edge is equal to the flow plus the already existing edge, so 20 plus 10, which is 30. And the forward edge from B to D would be 30 minus the flow, which is 20, so 10, and the backward edge would be equal to the flow, which is 20. The forward edge from D to terminal would be 0 and the backward edge would be 20. So this is what our residual network graph looks like. So as you can see, there are no more directed paths from source to terminal. So the algorithm terminates and we have the maximum flow for this graph, which is equal to 50. The runtime for this algorithm is equal to the number of iterations multiplied by the time it takes to do each iteration. The number of iterations depend on the choice of augmenting path we take. A good example for bad choice is this one. The notation here is a bit different. The first number corresponds to the flow and the second number corresponds to the capacity. So if you take an augmenting path A, B, C, D, the residual capacity is equal to 1. So we can push a maximum of 1 unit of flow along this augmenting path. So if we repeat and take A, C, B, D, again the residual capacity is 1. If you notice, C to B is a backward edge, so it will take, we are only pushing 1 unit of flow per iteration, and if we keep on doing this, it will take another 2000 iterations to complete. Whereas a good choice would be this one, where we are pushing 1000 units of flow along each iteration, so it will only take 2 iterations to complete. This is it, guys. Thanks for watching. If you have any questions, feel free to ask in the comments below.